Hey guys! It's our make fun of Maley moment, okay? Even though she doesn't watch these. And there's only about 12 of you that really do anyway. Maybe not even 12. Anyway, guys, hey, we're going to be in our examples today. Examples 1, 2, and 3.
Page 104, 105, and 106.
Lucky for you. Not 1, not 2, but 3 pages today of examples. 104, 105, 106. So go ahead, let's get open to those pages. We're going to hop right into it because, hey, we got lots of examples. We got a lot to do. Whoa, here we go. Oh, no, do we have volume, I wonder?
Will a one-variable equation always have only one solution?
I don't know.
Think about this question during the lesson.
Well, think about it.
The rectangle has a width of x and a length of 2x plus 3.
Mm-hmm.
The triangle has 3 equal sides that are 2x plus 2 long. For what values of x will the rectangle and triangle have the same perimeter? How can you use bar diagrams to represent the equal perimeters?
Okay, so folks, we got to remember perimeter, right? I know it's been a while since we've done this. Perimeter of a rectangle. Add up all of the sides. So we have 4 sides. We will come up with 4 expressions, and then we will add all of them together. The same thing is true for our triangle. We have 3 sides. We will take each expression. We will add them all together. All right, let's see what they do here.
You can draw bar diagrams to represent the perimeters.
Mm-hmm.
The top bar represents the perimeter of the rectangle with 2 sides of length, 2 times x, plus 3, and 2 sides of length x. The bottom bar represents the perimeter of the triangle with 3 equal sides of length, 2 times x, plus 2. Then, let's decompose and reorder the bar diagrams to figure out what the value of x is.
Okay.
First, separate each segment. Then group the variables and the constants. How do you know that the rearranged bar diagrams are equivalent to the original diagram?
We don't really. We're just hoping that they are. So no, guys, all they've really done is just breaking everything out into their numbers, into their constant and or variable terms. Yeah, everything's still good here. Don't worry. All good.
They show the same total number of x's.
Yep.
And the same constants. The expressions 6 times x equals 6 times x and 6 equals 6 are true for any value of x. This equation has infinitely many solutions.
What?
Another way to solve the problem is to write an equation that represents the equal perimeters. One side of the equation is the perimeter of the rectangle, and the perimeter of the triangle is on the other side.
This side.
You can solve by using inverse operations and properties of equality. For what values of x will 6x plus 6 equal 6x plus 6?
Okay, so guys, all they did, again,
Select
I
your answer.
know this is tough to see. All they've done is combine like terms on the left-hand side, that's for our rectangle, and the right-hand side for our triangle. And then it turned into these matching expressions, 6x plus 6 and 6x plus 6, right? We are going to go through that process of solving these equations. So guys, we have special case equations, right? Sometimes, most of the equations we've been doing get how many answers? 1. What we're going to find out today is that doesn't always happen. Sometimes we will get equations that have infinitely many solutions, right? Or an infinite number of right answers. And then on the flip side of that, we'll get some equations that have no answers. No answers at all, okay? So anyway, all values, I believe, is what we should be looking for here. Yes.
Now, use inverse operations and properties to solve.
Move the smaller variable.
6 times x from both sides.
Watch
then
what happens.
Simplify. So 6 is equal to 6. And because 6 equals 6 is always true, all values of x will make the equation true.
Okay.
This equation has infinitely many solutions.
Yes, it does. Okay, so guys, this is what we have to recognize. When our variable cancels out, like it just did in that example, that should alert me that something special is happening, and that's why this is a special case equation, okay? So when that variable cancels out, we should, bam, bam, let's get rid of all this. Don't care about all this, right? I like to make my own boxes, people. Okay. Again, you can fill yours in. They're going to be nearly identical, okay? All right, here we go. So we're going to solve this equation right here. So combine like terms. Nothing to combine here on the left. Okay? I have an x here, an x here. I need to combine those. Those will combine to 2x plus x is 3x. We're going to combine our numbers. Positive 10 plus 5. That's right, positive 15. Okay? All right. Here we go. Move the smaller variable. Maybe you look at it and go, I don't really know which one's smaller, so I'm just going to choose to move this one over here. So we're going to keep doing what we do, right? Anytime we go across that line, we've got to do the opposite operation. So this is a positive 3x, so we will subtract 3x. All right? My 3x's cancel out here. That's what I was expecting to happen. Okay, I'm just left with the number 15. Interestingly enough, my 3x's also cancel out over here on the other side. This is how I know, hey, lights and horns are flashing and going off, going, hey, hey, careful here, right? So yes, this does cancel out as well, and I'm just left with these two numbers. Now, I want to be clear, folks, just because your variables cancel out doesn't mean it's always infinite solutions. We then have to look right here and say, is this true or is this false? Do those numbers equal each other or do those numbers not equal each other, right? Because 15 equals 15, this is a true mathematical sentence. Because that is true, right, this equation has infinitely many solutions, okay? If we got two different numbers, like let's say this was 15 and this was 5, do those two numbers equal each other? No, they don't, and that's our other scenario. Hopefully, we'll see that here in just a quick bit, okay? All right, example 1 in the books. Moving on, example 2. Here we go. Ooh, we got another video. Special day. Usually example 2 is just words, not so much today.
Anna and Lee played soccer for the same number of hours one week.
Okay?
How many hours did Lee play on Sunday?
I don't know.
One way to solve this problem is to use a bar diagram. Draw one bar for Anna's schedule and another bar of the same length for Lee's schedule.
Okay.
Every day, Anna played soccer for X hours in the morning and 1 2/10 hours in the afternoon.
Again, we don't know how much in the morning. That's why it's
Copy
X.
each of Anna's soccer times from the chart to the bar diagram.
So
Now transfer Lee's soccer times to the bar diagram. Lee played soccer for X hours, 2 5/10 hours,
2 hours.
2X hours, and 4 5/10 hours.
Okay. Remember, our bar diagrams are equal to each other. So I think, right, they told us they played for the same amount of time. So Anna, we're trying to think of an expression that we could use to represent this entire bar. Just like Lee, we're trying to come up with an expression for that entire bar. I know you see it there in front of you, but let's take a look here and see what they do.
Now combine terms so that the bars match. In the top bar, use the commutative property of addition to group the 4 x's together and the 4 constants together.
Okay.
The sum of the 4 constants is 4 8/10. In the bottom bar, write 2x as x plus x.
Okay. That's fine.
And then group the 3 x's together and the 2 constants together. To make the bar diagrams match, borrow 3/10 from 2 5/10,
Whoa.
leaving 2 2/10. Then add 3/10 to 4 5/10 to make 4 8/10.
You guys know what X equals? It's right there.
Now 4 of the columns are matched. As a result, the remaining column must also match.
Yep.
The variable x equals 2 2/10.
That's right.
Another way to find x is to write and solve an equation.
This is what we've been
Anna
doing.
plays soccer
This shouldn't be
x
new.
hours, plus 1 2/10 hours, each day for 4 days.
Yep.
For a total of 4 times the quantity x plus 1 2/10.
Distributive property. We just did
Lee
this.
plays
folks.
soccer x hours, 2 5/10 hours, 2x hours, and 4 5/10 hours. His total soccer time is the sum of these terms. The two expressions are
That's
equal
right.
because Anna and Lee play the same amount of soccer during the week. To solve the equation, begin by using the distributive property to remove
Distribute.
the parentheses.
Combine your like
The
terms on
expression
the
on the
other
left
side.
side becomes 4x plus 4 8/10.
Yep.
Next, combine like terms on the right side of the equation.
Mhm.
The expression becomes 3x plus 7 0/10. Now
Can
use
we solve
inverse
this?
operations
Yeah.
to continue combining like
We
terms.
should be good to go from here,
Subtract
folks.
3x from both sides of the equation.
Yep.
And simplify. 4x minus 3x equals x.
1x.
And 3x minus 3x equals 0. Subtract
X is 1
4
and
8/10 from both sides. Simplify again to show that the equation has one solution. X equals 2 2/10.
Yep. Okay.
The solution to the equation shows that Lee played soccer for 2 2/10 hours on Sunday. The solution also shows the value of the other entries in the soccer schedule.
It's good stuff right there. Again, folks, this wasn't anything new. This was a normal one solution. So in 2-4, they're going to mix in those special case equations that we talked about just a second ago in example 1 with just our normal equations. They're going to try to fool us and make us think, oh, hey, we're doing something wrong. Okay? But guys, the thing I want you to notice, when your variables, right, from left side and right side, if you look at them, if they are different numbers, 3, 4, right? Just look at their coefficients. If their coefficients are different, we will always get one answer. Okay? It's only when they're identical will the variables cancel out, and then I have to look at those numbers. Okay? All right, so example 2, that's what we're used to. Let's take a look at example 3. Good news, there's example 4 as well. Okay?
Gil makes 3 bracelets and Mika makes 2 bracelets. They both use the same number of string colors. How many colors should they use to make the same amount of money?
I don't know. Okay. So Gil's bracelets are $5 per bracelet, okay, plus $2 for each string color. Okay. Mika's bracelets are $3 per bracelet and $3 per string color. Okay. So, bam. Again, maybe you didn't notice, they did Mika's equation right here, right? She makes 2 bracelets. We have 3 string colors. We have $3 per bracelet, right? If we look at Gil, right, same thing. Makes 3 bracelets. String colors are $2. Bracelet is $5. All right, so that's how they came up with writing each one of those expressions. Okay, I'm assuming, guys, they're going to solve this now. Wouldn't that be great if they did? Oh, look, there it is. Okay, so step 1, distributive property, folks. So we distribute a 3 on this side. It turns into this expression, 6x plus 15. Step 2 over here, distribute 2 on this side. It turns into 6x plus 6. Okay, so we get here. This looks like a variable on both sides equation. Okay, and it is. So what happens is, hey, we're going to move our x's together. But what happens, right, our x's both have identical coefficients. Positive 6, positive 6. When that happens, this is not a coincidence. This will always happen, guys. My variables go away. All I'm left with are my 2 numbers here, right? In this case, 15 and 6. Well, do those numbers equal each other? Of course they don't, right? So 15 does not equal 6. Therefore, no matter what we do, there is no solution to this equation. Okay? No solution. Okay? When your variable cancels out, it doesn't necessarily mean one or the other. You have to make sense of those 2 numbers. How many solutions does this equation have? All right, I'm not sure, but we're going to solve it together, okay? Step number 1, combine any like terms, okay? So nothing for me to combine here. This is just 4x plus 8. All right, on the right-hand side, we can go ahead. We can combine this. This term and this term, okay? So I'm going to say, yep, 3. Nobody combines with 3. 0.1 plus 3.9 is, oops, we need a sign here, is 4.0. Just call it 4x. Okay. Keep solving your equation, guys. We're going to move a variable. I'm going to choose to move this variable over here to the right. Okay. So it's a positive 4x, so we're going to do the opposite. That's negative or subtracting 4x. 4 minus 4 goes away. All I'm left with is this 8. Okay. Didn't do anything with 3. Ooh, what happens here, guys? 4 minus 4 cancels out. All right, so again, we just talked about it. When your coefficients are identical, 4 and 4, right? Well, really, you can think of it as positive 4 and positive 4. When they're identical, this always happens, right? They cancel out on both sides. I'm left with this. This means special case. Is it true? Is it false? Mr. Knoll says thumbs down. I don't know what that means.
False.
Okay, so if it's false, we got to put a 8 is not equal to 3. And because those two numbers do not equal each other, guys, you guessed it. This is a no solution equation. No answer to this one.
None?
Nothing. Can't do it. Can't be done. Good news, right? This is like bonus time. This is like when the game goes into extra innings or it goes into overtime, guys. Here it comes. Overtime in the form of example 4.
Four
Yes.
of them.
4. This is the first time all year we've gotten this. Okay? Yeah, that's good stuff. All right. How can you determine the number of solutions each equation has without solving? If you've fallen asleep for this whole thing, guys, I need you to pay attention here. Okay? So this is your secret to how you can figure this out with really out doing too much work. Okay? Think about what each one of these has, right? We need to simplify or combine like terms or use the distributive property to see what we have, okay? So I think they're going to do that for us here. Maybe? They are. That really
Load.
it did not load. You guys want me to go back and try again?
I think it did load. That's just how it loads.
Okay. Well, guess what? I don't really like the way they had it. I'm cool with this right here, guys.
Do some clicking and dragging.
Oh,
You
we're going
can
to do
drag those over there.
Yeah, we can, but we need to figure out first, though, guys, what does all this turn into? So this turns into x plus 10, right? I just combined these here. Combine your x's over here. 2x minus 1x. Oh, yeah, that's x. And this is minus 10. All right? Now, we know we're going to compare coefficients in our variable terms. Are they identical?
Yes.
Yes, they're invisible ones, folks. All right, so we know this is a special case scenario. All right, so then you would just look at this number 10 and this number negative 10. Do those two numbers equal each other?
No.
No, they don't, right? Because they don't, bam, look. There, is that what you wanted, Mr. Knoll?
Yeah.
Yeah.
That's a no solution.
Yes, this is a no solution one, okay? Same thing here on letter B, or number B, as I like to joke around and say. This should turn into 3x plus 12, right? Also equals 3x plus 12. Yeah, we recognize positive 3 is our coefficient in both of these variable terms, right? So these are going to be identical. Guys, use the flow chart that we gave you, right, to help you out with this stuff. So, hey, are my coefficients identical? Yes or no? Boom, go here. No, go here. Is this true? Is this false? Okay? Last one here. Nope, don't even have to do anything. Already simplified. 5x plus 8 equals 2x minus 1. Do you have matching coefficients in your variable term?
No.
5 and 2 are not matching the last time that I checked. So when that happens, guys, you will always get one answer. Always get one answer.
1.
1. The favorite number 1.
How about
Okay.
we do a try it?
Would you like to do the try it?
Let's do the try it.
Okay.
Let's determine without solving.
Okay. Determine without solving.
Now that part there at the bottom,
Yeah, that
that's
goes
supposed
over
to go
here.
there for letter C.
Yeah, they didn't do a very good job of writing this. We're going to give them a not good grade.
5x minus 4 plus 4x.
Okay.
Mr. Freaky's now going to make that disappear. Watch this, everybody. Wow.
Okay.
Wow. That's cool.
Awesome. All right, so let's start right here, folks. So we're going to take and combine any like terms. Nothing to combine here. Nothing to combine here. So I want you to look at these two terms. My variable terms, our coefficients. Are they identical? Are they different? That's
Different.
Right. Different. Different means one solution. Did it ask me to find that answer?
No.
No, it didn't, right? Sometimes, guys, they just want to know. So I'm not even going to bother solving it. Here, before you can use the flowchart, you have got to distribute. You've got to simplify. Combine like terms, whatever the case is. Here I need to distribute a 3. This is going to turn into 3x plus 6. Okay? Now we can use our flowchart. Look at your variable terms. Are your coefficients identical?
Yes.
They are. Positive 3, positive 3. Okay, we know they're going to cancel out. Look at your numbers. 6, negative 6. Are those the same? Are those identical?
No.
No. No, they're not. Use the flowchart. No solution. Gee, I wonder what the last one could be. I don't know. Okay. Nothing to simplify here. But I can do some simplifying here. 5x plus 4x. Right? Mr. Knoll loves to put little boxes around stuff. Okay?
That's right.
So we're going to combine these. So make this go away because I need some more room. All right, so here we go. 9x minus 4. Combine this. Also 9x. Bring down this 4. Okay? Look at your coefficients in your variable terms. Are they identical?
Yes.
They are. So look at your numbers now. And you've got to make sure you pay attention to the signs here. So negative 4 equals negative 4. Is that true? This is true, guys. This is a infinitely many solutions. Okay? Bad news. That's it for examples 1, 2, 3, and 4, guys. We don't have any more solutions. We don't have more examples to do. We're all out, okay? But good news, we still have key concepts. We still have our Math Excel, our additional practice, all that other fun stuff to get into. So don't worry. I'm sure you had a blast, just like me. We're going to get into more of that here in just a second. Have a great